Hello, my name is Diana Fisher. I have been asked to present on the system dynamics work I have done with secondary school students and teachers over 3 decades. I have used system dynamics modeling in my mathematics and modeling instruction for 30 years. Although science instruction is the most natural discipline for SD modeling, I would like to make an argument that if we really want SD modeling to become a more mainstream analytical tool, it should be embedded in secondary school mathematics. SD modeling can reinforce important mathematical concepts quite well. Dr. Barium specializes in the study of complex systems. To be able to analyze complex systems, he claims that calculus and statistics do not have the tools to describe what we want to study, that we need to work with new concepts, that we need to ask different questions about system dynamic behavior. He says working with complex systems changes how we think. We have an opportunity to help our mathematics students broaden their thinking to encompass techniques that will help them think about complex dynamic problems. One way to start is improving their understanding of functions. Studies in the United States indicate that students possess weak understanding of functions. Over the last several decades, mathematics instruction in the U.S. evolved to require multiple representation of function behavior, including graphs and tables. But now research indicates that mapping diagrams also provide a rich foundation for understanding functions. The late Dr. James Caput proposed democratizing the concepts of calculus by providing technology-based learning environments. He said new notation systems with new ways of acting upon those new notation systems offer dramatically new possibilities for mathematics learning. SD is such a new and powerful notation system. The audience recognizes these system dynamics modeling icons from which SD models can be constructed. The stock, an accumulator, represents a main function in the model. Mathematically, it operates as an integral does in calculus. The flow is the rate of change of the stock, so it is essentially the first derivative described in calculus. Converters hold constants, parameters, or simple arithmetic combinations of model components. The connector indicates the influence of one model component on another. Mathematically, the connectors identify the dependencies of one variable on another. I will not take you quickly through the two most basic functions studied in algebra, connecting SD and traditional mathematics representation. Suppose we were interested in how water in a lake is increasing based on water flowing in at a constant rate. Using the SD structure, the initial water in the lake would be placed in a stock icon, and it would only have an inflow since it is only increasing with a constant value in the flow. We know the behavior of the stock is growing linearly since the rate of change is constant and positive. The SD software calculates the value of the stock using recursion, which is shown in the table at the left. We see that the flow value is added to the current value of the stock each time unit. Now we see the traditional closed form equation for the linear function, where W represents the amount of water in the lake. It starts at 100 units and grows at 5 units per year. If we were to construct what we know is an exponential population growth behavior, we could start with a stock of elephants and an inflow of new elephants born to this herd each year. But this model is not correct. We know the inflow cannot be constant because the number of new elephants born per year depends on knowing how many elephants are currently in the herd. So we now indicate that dependency with a connector. Oh, and now we have introduced a feedback loop. The loop is reinforcing because the more elephants in the population, the more new elephants are born per year, adding more elephants to the herd. But this model is still not complete. We should indicate the number of new elephants born per elephant in the herd each year. We do that by indicating a birth fraction in decimal form that will be multiplied by the number of elephants in the herd each year. So for exponential growth, the inflow is proportional to the current amount of the stock. Or mathematically, the rate of change, the flow, is defined as the stock value times some growth factor value. This is exactly the differential equation that represents exponential growth. But algebra students don't need to know that they are learning calculus. They are just learning a different behavior pattern over time and how to create it based on its rate of change definition. Again, quickly, we would have our stock flow definition as shown with a 20% growth fraction. The elephant population will grow exponentially because the inflow is proportional to the stock value. If we think about what the SD software is doing, we look at the recursion in the table. The flow calculates the growth amount and adds it to the stock each year. There are two equations that are possible mathematically. The easier equation is represented at the top and is the one often taught in first-year algebra. It is often used when we want to calculate values once every year or time unit. The second is shown at the bottom and is often used in situations where calculating continuous change is a better choice. The top equation is probably the best choice for this particular elephant herd example. In SD modeling, we use the same diagram for each scenario and merely increase the number of times the simulation calculates the values each time unit to differentiate which situation is being used for calculation. It is a much more intuitive process, in my opinion. Just so you know, there is a free web-based version of the SD modeling software that works on tablets, computers, laptops, Chromebooks, and smartphone that will allow you to have your students build these models if they have access to this technology. Go to publish.icsystems.com. The software is called Stella Online. Once students learn linear and exponential model structures, they can start putting them together to study new problems they could not study with equations. I have used these medication models in my algebra classes over many years. Students really like them. Consider an emergency room problem. You, the student, are a medical resident working in the emergency room, and a patient comes in who needs immediate medical attention. From your analysis, you decide to connect this patient to an IV drip that will supply 1 milligram of therapeutic drug per minute. This person, you estimate, will metabolize the drug at about 0.55% per minute. What is the pattern of the drug level in the body over 24 hours? So the diagram might look like this, with an inflow of medicine and an outflow of body using and eliminating the medicine. Observe the left side of the diagram. Since there is a constant inflow, the left part of the diagram is similar to a linear model structure. Observe the right part of the diagram. The structure is similar to an exponential decay. The drug is lost as a percent of the current amount of drug in the patient's systems. Students try to predict the behavior of the drug in the body over time, giving a reason for their predictions. Then they build the model and see what the computer produces. Then they have to explain why the computer graph has the shape that it shows. Skipping the second medication scenario, we will go to the third drug model. It involves taking medicine in the form of pills. It has been a busy day in the emergency room. A third patient arrives, and you decide to give this patient 2 pills of 375 milligrams each of a therapeutic drug and tell them to continue taking 2 more pills every 4 hours. This person, you estimate, will absorb the drug from the stomach in the bloodstream at about 4.5% per minute and metabolize the drug at about 0.55% per minute. What is the pattern of drug level in the body over 24 hours? This model uses two stalks because the medicine must first accumulate in the stomach and then move into the bloodstream. The inflow is a pulse because the pills are taken once every 4 hours. Students are asked to anticipate the pattern of behavior of just the left part of the model drug in the stomach. Then students are asked to anticipate the pattern of drug in the blood over time. This is not a trivial analysis. Then different patterns of pill delivery protocol are explored and compared to the optimal therapeutic level for this medication. Finally, in this sequence of medication models, students as a class are asked to help modify the pill model so that it will calculate the blood alcohol concentration of a human male sipping beer over 2 hours. The modified stock flow diagram is sketched as a class. Then students access the pre-built model online and test the following scenarios using the model. Influence of body weight, gender, type of alcohol, and type of drinker. Now let's turn to a different sequence of models. The basic population model is ubiquitous in system dynamics studies. Problems in health, economics, environmental science, biology, geography, sociology, and mathematics, and more often involve the study of population dynamics. The basic population model involves a stock for population, since that's the value that we want to track over time. It is the function. An outflow of births and an inflow of births and an outflow of deaths, and their attendant births and deaths fraction. The basic model contains two feedback loops that control change in population dynamics over time. There are three types of graphs that this structure could produce based upon which feedback is dominant. Assume that the birth fraction is larger than the death fraction. The model could produce exponential growth, but the deer population cannot grow forever. There are limiting factors that would influence the growth. As the deer population increases, there would be more competition for food and water. Deer could become more aggressive as they vie for the limited resource. Overcrowding can also lead to aggression and to the spread of disease as waste builds up in a limited area. Each of these factors would lead to a higher death rate for the deer. Assume that the environment can support only a specific number of deer. The number of deer the environment can support in any given location is called the carrying capacity. We assume that the carrying capacity value is unchanging. As the population grows toward the carrying capacity, the death fraction is being increased as we think it should. The deer population graph looks reasonable with the carrying capacity component. At the beginning, there are few deer, and the population is growing quite a bit. As the population gets closer to the carrying capacity, the growth slows down eventually, moving to steady state. This demonstrates transfer of feedback loop dominance. Now look at the typical closed form equation for the same scenario. It seems to me that the stock flow model is easier to understand and interpret, making this scenario approachable by students in mathematics classes lower than pre-calculus, where the equation is usually studied. I have used this model in my algebra classes successfully with students as young as 15. So now we get to the meat of this presentation. What overarching value does SD modeling approach add to mathematics instruction? A new representation for some core functions studied in algebra and pre-calculus provides not only a different representation that is more visual for the functions, but bases the new representation on the rates of change for each function, a very important concept in calculus. The structure, the blueprint for each function, helps describe why the function behavior makes sense. That is, constant flows create linear stock behavior. proportional flows create exponential stock behavior, etc. Each system dynamics icon uses full words or phrases in their names, making it easier to remember what each part of the model represents. And it has been my experience with students that they have a much easier time translating word problems that describe dynamics to the SD model structure. Take, for example, the representation for an oscillating spring behavior. The stock flow diagram captures the concepts of position, restoring force, mass, acceleration, velocity, etc., all central concepts in the dynamic of a bouncing spring. The closed form equation merely captures the appearance of the oscillation, not the core structure that is causing the behavior to occur. I believe that the stock flow structure is more educationally valuable than the closed form equation. Students and many adults are notoriously poor at reading and interpreting graphs. SD modeling has one of its main analytical techniques to interpret the graphical output of the models multiple times as models are built, modified, and tested. Students get lots of practice reading and interpreting graphs. Moreover, students are often required to view flow graphs on the same grid as stock graphs to help explain stock behavior. This correlational graphical analysis is a core concept in calculus and very important for understanding dynamic phenomenon. Creating the stock flow diagram lays bare the student's mental model. The student can test his or her mental model to determine if the structure produces reasonable results. Then, if it does not, the student knows he or she must modify the model structure via more research that often includes communicating with other team members to improve the model and obtain reasonable results. As you have seen, building useful and interesting models using SD modeling can allow students to build problems that would be out of their reach using only closed form equations. This makes a much larger pool of interesting problems for students to study and makes connecting mathematics with real world more obvious. Another factor that is outside current mathematics instruction at the secondary school level is the importance of nonlinear system behavior, which is necessary to produce transfer of feedback loop dominance, and of course the inclusion of delays. The model on the left has been built and analyzed by non-honors algebra students, and the delays represented on the right, both material at the top and information delays at the bottom, could be understood by algebra students. This slide identifies two websites with resources that you may find useful. The first is a website that contains some free SD lessons for use with secondary school students, as well as where to purchase some books of SD lessons that are published. It also contains examples of secondary school students' original SD model diagrams and technical papers explaining the models. It advertises online SD courses geared to secondary school math and science teachers and shows the alignment of SD with U.S. national educational standards in many disciplines. The other website contains additional lessons that can be downloaded or purchased and numerous lesson books appropriate for pre-college students. The experience that greatly enhanced my opinion about the virtues of using the system dynamics modeling approach with students occurred when I saw what students could produce when given the freedom to choose a dynamic problem that interested them, for which they could create an original model, write a technical paper explaining their model, and present their model to an audience. I wanted to prepare students to identify and analyze problems in the world from which they could gain an understanding by building system dynamics models. I wanted them to develop skill in model building, in analyzing model design, in output and feedback and in explaining what they learned. So I designed a secondary school system dynamics modeling course that I taught for 20 years. One of the most important lessons I included in my SD modeling course was to show students how to translate a systems problem found in a news article into a stock flow diagram. Students listed the most important variables. They built the structure of their model by hand, and they also sketched out the feedback. Students indicated that this was one of the most important lessons in preparing them to do their final project. I'm going to magnify this bottom part so you can see it a little bit better. I know it's blurry, but it's because I just used the previous picture to magnify it. But you can see the design of their model structure. You can see their feedback loop. They're doing behavior over time graphs. All of this was part of the lesson for analyzing an article in the news. I'm now going to show you some sample student original SD models. In 2007, when the United States was experiencing an oil crisis, this student observed that many people were trying unsuccessfully to buy hybrid cars. This was his idea of why the problem happened. It actually is broken into 3 segments. There is the hybrid car segment at the top. I'll go back. Hybrid car production, hybrid inventory, and active hybrid vehicles. There is a factory capacity, which was a limiting factor on being able to produce enough cars. And then there was a backlog of orders and perceived backlog that prospective buyers weren't going to get a car very soon, even if they ordered one. His model did not start in equilibrium, unfortunately. So let's ignore the first part of this graph and focus on the spike in oil prices at week 30. The new demand, which is the pink curve, spikes upward for hybrid cars. That is quickly followed by a spike in the backlog demand for hybrid cars, which is the brown graph. The price of hybrid cars, which is the green curve, shows an increase as backlog increases. The blue line, which is on a scale by itself, is the number of active hybrid cars, and that is steadily increasing. The first year I introduced material and information delays to my students, many students understood the ideas immediately. This student started his model on workforce pressure using the idea of 3 delays. So here we have employees who are being hired and fired. This is the amount of work that the company wants done. This is the perceived satisfaction of the current working people. And up here is the pay that is given to the workers. The 3 delays here are an information delay down in the perceived satisfaction, an information delay in hiring, and a material delay in the actual amount of work that is being completed. This student who did the workforce pressure model did start the model in equilibrium. In week 4, the amount of work, which is the red graph, is increased significantly, causing a drop in perceived worker satisfaction, that's the green graph, until management starts to hire more people, that's the blue graph, to help with the extra workload. With more people, the work that has piled up is starting to decline, which causes the perceived worker satisfaction to start making a comeback. 2 freshmen created this model about different ways to travel to work in Portland and used data from the Portland Transit Department. They did an excellent job of capturing the type of commuters we have in Portland and how the increase in traffic loads leads to longer commute times. This comment was written in a paper by one of my modeling students. In other classes, I am often asked to posit logical solutions to problems, or am given the solution reached by other people. Using models of complex systems, I can test my own theories and confirm those of others instead of faithfully accepting them as fact. Where other classes ask me to memorize, this one dares me to explore. The work of these secondary school students shows what students anywhere could do given the opportunity to learn the methods that will help them analyze some of the difficult problems they will face as adults. I created a website so it would be easy to show decision makers the value of this type of instruction and to let them hear the students speak about their models. I hope it will provide the stimulus to make these opportunities available to more students. I believe that modeling dynamic systems really does provide us a different way to think about problems. And a favorite quote of Einstein's is, "We cannot solve our problems with the same thinking we used when we created them." Thank you.